Hi guys, in this video I'll introduce alkenes. We'll talk mainly about nomenclature of alkenes, and we'll also look at the potential for cis-trans isomers with alkenes, and we'll learn the easy terminology for identifying the different stereoisomers of alkenes. First, a couple of introductory alkenes. The simplest alkene would be ethene. You have to have two carbons to have the alkene double bond. Ethene, also known as ethylene. Ethylene is a gas. It used to be used for ripening of fruit. It actually still may be used for that purpose. How? Well, that's a biology course. It used to be used as an anesthetic to sterilize surgical instruments. I don't believe it's used much for that purpose anymore. Of course, ethylene has formula C2H4. We see 1 degree of unsaturation both in the structure and formula. A more complex or larger alkene would be the breast cancer drug tamoxifen. We see the alkene here. Tamoxifen also has the ether group and then the tertiary amine out here. We also have two benzene rings or two phenyl rings. One thing we can make note of here is that although the benzene ring does contain 3 pi bonds, which looks like alkenes, we will not consider these alkenes. The pi bonds within the benzene ring have special structure, special bonding, special reactivity. Those are aromatics, and those alkenes, or those pi bonds, are not considered as alkenes. So truly the only alkene here is right here. And so tamoxifen does illustrate or have an alkene in the structure. Okay, let's look at naming of alkenes. Nomenclature of alkenes is very similar to nomenclature of alkynes. We start with the longest continuous carbon chain. And so in this example right here, longest continuous chain would be 1, 2, 3. 1, 2, 3, 4, 5. So we would have a 5. Importantly, the alkene double bond must be within the longest continuous chain. Because of that, you might as well start here. 1, 2, 3, 4. Either way you go 5. And so we can circle there, sort of right through here. We have a 5, which is going to be pentane, okay? But because it contains a double bond, we're going to use the ene ending instead of the ane. So I'm going to get rid of this, and this is going to become, I'll write it here, pentene. So we have circled a pentene. We also need to denote here where the double bond is, because the double bond can be at different positions within the pentene. For example, we could have a pentene with the double bond here. Here the double bond is said to be at the 1 position. Okay? Carbons of double bond get lowest possible numbers. We almost treat the alkene like a substituent. The alkene is between the 1 and 2 position. We only denote the first number of that positioning. So this is going to be a 1 pentene. This example here would be a 2 pentene. And so this would be a constitutional isomer. It has a different name. Has different connectivity. Here the double bond is connected between the 2 and 3 carbons. Here the double bond is connected between the 1 and 2 carbons. We just use the first number in our name to denote where the alkene is, 1 pentene. That's circled. What is on our 1 pentene? We have a methyl group. What position? 1, 2, 3, 4. So this would be 4-methyl 1 pentene. So here's our name for this guy here. Why did we not start over here? Because we want double bond to get the lowest numbers. Carbons every double bond gets lowest numbers, so it was a 1-pentene double bond designated by first number of positioning. If there were a choice, we would then give the remaining subs lowest numbers. We may see a choice in subsequent examples. Okay, let's name this guy over here. Longest continuous chain, 1, 2, 3, 4, 5, 6, 7, 8. I don't see any other 8. The problem though, that 8 does not contain the alkene. The alkene must be within the longest continuous chain. We might as well start here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. And so we have a 7 here, a 7-carbon chain with an alkene. That's going to be called a heptene. We have to denote where the double bond is. The double bond is at the 1 position. 1, 2, so 1 heptene. What we have there is a 1 heptene circled. What is on our 1 heptene? We have this propyl group at the 1, 2, 3 position. So we have 3 propyl, 1 heptene. Let's name this guy here with the chlorine. Longest continuous chain. 1, 2, 3, 4, 5, 6. Any way you go at 6, we can circle right through here. And so we have a hexene, 6-carbon chain with 1 double bond, hexene. Where's the positioning of the double bond? If we start on this end, it's 1, 2, 3, 4. Okay? 3, 4 if we start on this end. If we start on this end, it's 1, 2, 3, 4. Okay, so which end? If a choice, give subs lowest numbers. If this is the end, either way you go, it's a 3-hexene. Let's go ahead and put that. Either way you go. So we got that much there. Which end is truly number 1? Over here. If this is 1, we have subs at 2, double bond at 3, and then 4. And so that would be a methyl and chloro. Chloro comes first, 4-chloro, 2-methyl, 3-hexene. If this was the 1 position, it would have been 3-chloro, 5-methyl. So our substituents would have been 3 and 5 instead of 2 and 4. 2 and 4 is better than 3 and 5. So there's our name. Now in this compound, we're going to need a stereochemical descriptor to go with that, because this alkene is stereogenic. That alkene is not. That alkene is not. Stereogenic will be defined a little bit later on the next page. We'll come back to this and we'll have to add a stereochemical descriptor in front of this name because this compound has potential for stereoisomers. Because of the alkene leads to stereoisomers. That's what genesis means. It leads to the stereochemistry. Let's do the next example. Longest continuous chain, well, 1, 2, 3, 4, 5. So there we go. So we have a, put it right here, pentene. The double bond is at the, not the 1 position, but at 2, 3. It's going to be 1, 2, 3. Double bond gets lowest numbers. We would not come over here because then the double bond would be 1, 2, 3, 4. 2, 3 is better than 3, 4, but we only list the first number. We have a 2-pentene. What is on the 2-pentene? I have a bromo at the 1, 2, 3, 4, 5. So we have 5 bromo. 5 bromo 2-pentene. Let me erase this here. For this guy here. See, a lot of students try to call this the 6 carbon or something. 1, 2, 3, 4, 5, 6. And a student may say that's a hexene. It's obviously not a carbon. This is a substituent on the 5th carbon. This alkene is also stereogenic. We will have to come back and add a stereochemical descriptor to that after we cover what this means on the next page. Let's look at cycloalkenes. We can have carbocyclic rings with a double bond. In this case here, we have a cyclohexane with a double bond. So this is going to be a cyclohex, not ane, but because it contains a double bond, cyclohexene. Okay, that's cyclohexene. What is on the cyclohexene? A bromo and a propyl. What's the 1 position? Okay, well, alkene gets lowest numbers. So we're going to make it 1, 2. But is it going to be 1, 2 that way or 1, 2 this way? Either way you go, it's a 1 cyclohexene. But that 1 doesn't need to be written because it's always assumed that the 1, 2 is where the double bond is. But which is which? Well, from there subs lowest numbers. If that's 1, 2, that would be 3, 5. Okay, 3, 5. If this is 1, we get 1, 2, 3, 4, 6. Okay, 3, 5 is better, so we want that to be 1, 2, 3, 4, 5. And so we have a 3 bromo, 5 propyl cyclohexene here. Again, the position of the double bond is not needed. In this example. Let's try another one over here. What size ring do we have there? It's a 5-membered ring, so it's going to be a cyclopentane. But we're going to change that ane ending to ene because we see the double bond. And so this is going to be cyclopentene. That's cyclopentene. Obviously a chloro and an ethyl. What's the numbering? Is it going to be 1, 2, or is it going to be 1, 2? If that's 1, we have substituents at 2 and 4. Now if this is 1, we have substituents at 1, 1, and 4. Note, if this is 1, you can't go this way and call that 1, 3. The double bond has to be 1 and 2. If this is 1, we have to go this way to make that 2. Oh, that's 3 and this is 4. Okay, which is better, 2,4 or 1,4? 1,4 is better. So that's going to be 1, 3, 4, and we end up with 1-chloro, 4-ethyl cyclopentene. Okay, there are some common names to know involving alkenes. If you just have a plain alkene coming off of something, where this is an H, that's an H, there's an H here, that's called a vinyl group. Okay? And you can use this common name terminology like in this example. Vinyl chloride. Just got the vinyl group, bonded to a chlorine, vinyl chloride. If you polymerize vinyl chloride, you get polyvinyl chloride, PVC. Now, if we have the plain alkene CH2 and then a group, that there is called an allyl group. Allyl. For example, you can have allyl alcohol. If that was a chlorine, it would be allyl chloride. So the vinyl and the allyl are two fragments containing the simple alkene, and this terminology you should know. Okay, a very important structural feature of alkenes is the possibility of having stereoisomers. For example, this is 2-butene. 1, 2, 3, 4, double bonded 2. This here is also 2-butene. 1, 2, 3, 4, double bonded 2. But these are two different compounds. Here, the two methyls are trans about the double bond, or on opposite sides of the double bond. We've seen the terminology trans before. Where in this 2-butene, they're cis. They're both on the same side of the double bond. Now when I say side, I'm not talking about this side versus this side. I'm talking about two different carbons. They're on the same side in that regard. Okay, these are two different compounds. Now over here, we can draw a butane in this manner or this manner. Well, that's just the same compound. That's just butane in two different conformations. We talked about conformations. I mean, that conformation there is sort of an anti-conformation. That's why we do the zigzag, so the groups are anti. Okay? Here, that's where this group is rotated up. And that's an eclipsed or syn conformation. But that's just conformations. That does not make it a different compound. Okay? But over here, these guys are stuck in this so-called conformation. But it's not a conformation. There's cis, here's your double bond, and then here's trans. Okay? And if we look at the cis, this cannot rotate and become trans. The reason why is, because if you remember the pi bond is side-to-side overlap of p orbitals. And if we try to rotate this, we're going to have to break the side-to-side overlap, and that's just not going to happen unless we put a lot of energy in, and then we're talking about doing chemistry. But this compound is fixed there. These two groups are fixed cis. These These two groups are fixed trans. Because of that, these are two different compounds. Okay? Now, they're quite similar. First of all, what is the relation? They are isomers. I mean, this is C4H. C4 saturated would be 10. This has 1 degree of unsaturation, so this should be C4H8. This is also C4H8. Okay, so they're isomers. What type of isomers are they? Do they have the same connectivity? They do have the same connectivity. That's why they have the same name. 2-butene, 2-butene. If they have the same name, that means they have the same connectivity. So they're not constitutional isomers. What type of isomers are they? They are stereoisomers. They only differ in the way these groups are projected. In both compounds, we have a methyl here and here. Methyl here and here. So they're connected at the same way. But here the two methyls are oriented both the same direction, where here they're oriented opposite or trans, and they're fixed that way. Because of the lack of rotation, this is two different compounds. They are actually stereoisomers. Okay? Cis-trans stereoisomers. Because they're different compounds, they're going to have different physical properties, such as different molecular dipole moment, different boiling point, different melting point, etc., etc. Different densities. Two different compounds. Where this over here again is just the same compound, just with different conformations. Okay. Now in this particular case, it's pretty easy to say this is cis and that's trans. The orientation about the double bond. But what about this guy? Is this cis or trans? Okay? Cis or trans doesn't work here, because if I call this cis, well, the methyls are cis, okay? But the methyl and chlorine are trans. So what do you call it? Do you call it a cis compound or a trans compound? Well, actually neither. Cis and trans is only useful when you only have two groups. If you have more than two groups, we're going to use the EZ nomenclature. Okay? Let's look at how to do the EZ. By the way, before I go on, we'll use this term again. We've already used it. It's stereogenic. This alkene, the presence of it leads to stereoisomers in that case. If there was no alkene, you would have no stereoisomers. That's the same compound. The presence of the alkene leads to stereochemistry. We now have two different stereoisomers. We call the alkene stereogenic. What we're going to have to learn going forward is when is an alkene stereogenic and when is it not? Because it's not always stereogenic. Okay, let's see if we can do the EZ nomenclature. Let's do this example here. Same compound. Same compound. First thing we're going to do is assign priority to the groups on each end of the double bond. This end versus that end. We assign priority based on atomic number. Higher atomic number, higher priority. So what we're going to do on this end, what is the alkene carbon bonded to? It's bonded to a carbon and hydrogen. Which one has a higher atomic number? That would be carbon. So I'm going to start. Higher atomic number. Over here, the alkene carbon is bonded to chlorine or carbon. Which has a higher atomic number? Chlorine. So I assign priorities. And my dots did not move. Assign priorities, chlorine, this end here. Okay? Now we want to look at how to eventually get the name here. We call it E when the high priority groups are on opposite side. We call it Z when the high priority groups are on the same side. In this example, the high priority groups are on opposite side. This side versus that side. Okay? The high priority groups they're like they're trans. But when the high priority groups are trans, we don't call it trans. Instead, we call it E. So this example is E. So, if we look at the name of this compound, let's name it. Compound up there. That's going to be longest continuous chain, 1, 2, 3, 4. Double bond at the 2 position, so this is going to be a 2-butene with a chlorine. Let's call this 1, 2, 3, 4. The chlorine at the 2. 2-chloro-2-butene. But what we're going to do is we're going to put an E in front of that. The E sometimes is put in parentheses. I don't think it's required. E2-chloro-2-butene. Because, let's look at this. We can have the same compound like this. So that's E. What would be the name of this compound here? Well, that's also 1, 2, 3, 4. 1, 2, 3, 4. 2-chloro-2-butene. So this guy, is this E or Z? High priority group on this end, chlorine. High priority group on this end, carbon, or H, carbon. So over here we see the high priority groups on the same side. We call that Z. So this one up here is Z, and the same exact name. Okay? These two here are stereoisomers. Because this methyl cannot rotate up and be beside that other methyl because of the lack of rotation because of the double bond. One is called E, and this is a stereochemical descriptor that we put in front of our stereoisomers. Stereoisomers always have the same name, they just differ by some type of stereochemical descriptor. Okay, let me give you a little tidbit of how to remember these. How do I remember E is opposite? E is a vowel. Opposite starts with O, a vowel. Z, I remember that because the high priority groups are on the same side. Z, the same side. Okay? That's how I remember E and Z. Now, let's practice E and Z with these examples here. Let's do the first one here. E or Z. High priority group on this carbon, F or carbon. F has a higher atomic number. Higher priority group on this carbon, bromine or chlorine. That would be bromine. High priority groups are on the same side. Z. Now, if you can label one as Z, that means you can also label it as E. That means it will have a stereoisomer. The stereoisomer of this will be chlorine there, bromine here, F here, methyl there. This would be E, because F for carbon would be F, chlorine or bromine would be bromine. Here they're opposite, E. These are different compounds, because here the F and the Br are on the same side. Here they're on opposite sides, and this is fixed because of lack of rotation. Two different compounds, stereoisomers, one labeled Z, one labeled as E. Otherwise, they'll have the same exact name. Let's do this guy here. On this end, F or carbon, F. On this end, H or H. That's an H there, right? All right? H or H. There's no answer. They're the same. How are we going to do E or Z? Well, we can't. And this should tell us, or tells us, this alkene is not stereogenic. There is no cis-trans isomer here. Why not? If we drew this alkene with the alkyl group up and the fluorine down, it's the same compound. That's the same compound. It's just flipped over. It's like drawing my hand on the board like this and then drawing it like that. Okay? You've got to realize that these are the same compounds. This alkene is not stereogenic. And it's the presence of that alkene in this particular case does not lead to stereochemistry, does not lead to stereoisomers. Same compound. But here's how you tell when an alkene is stereogenic or not. If you can do E and Z, that means you have both E and Z possibilities. If you cannot, as in this case, that's going to tell you that there's no possibility and there's no stereochemistry about this double bond. So what was this one here? This was F and Br. I believe that was Z. This is neither. How about this guy? Chlorine or carbon? That would be chlorine. Carbon or carbon? It's the same. Now there's important here. If this chain was longer, that would matter. We'll see examples of that down here. But these groups are identical. Not only are they carbons, but it's just identical groups. Because of that, you cannot do E or Z. You cannot determine or make a distinction on that end. That should tell us what? There's no stereoisomer here. So this is also neither. Neither one of these alkenes is stereogenic. That is, if we switch the position, if we put the chlorine here and the propyl there, it would still be the same compound. You'd still have a chlorine next to a methyl and trans to a methyl, just like you have here, next to a methyl and trans to a methyl. So neither of these are stereogenic. This alkene is stereogenic. What about tamoxifen back on the first page, the breast cancer drug? Is that E or Z? Double bond here. Let's look here on this end. Oxygen or carbon? High priority group would be oxygen. We look at the first atom attached to the alkene carbon. Let's look over here. Carbon or carbon? Okay? Well, that looks like they're identical and we can't decide. Actually, we can decide here because these two groups are not the same. Okay? And indeed, if you drew tamoxifen with, I'm going to denote the benzene ring as phenyl. That's very common. If we put the phenyls cis to each other, these are not the same. Here the phenyls are cis, here the phenyls are trans. Okay? Otherwise, they have the same exact name. These are stereoisomers. What do we want to call this one? One of these is going to be E and one of these is going to be Z. How do you do this here? Okay? If the first atom doesn't give you a win, they're both carbon, you then look at what's bonded to that one. Okay? And we're going to list the three things out. There's three things bonded to this carbon. What are they? For this one here, carbon, H, and H. Bonded to that carbon are carbon, H, and H. There's two H's there. We want to list these with the high priority atom first, with priority based on atomic number. Okay? What's bonded to this carbon? What are the three things bonded to that carbon? Carbon. Now that's a double bond there. Okay, that double bond is supposed to be here. All right? This carbon is single bonded to carbon, double bonded to carbon. A double bond to carbon counts as two bonds to carbon. So really, all three of those are carbon, carbon, and carbon. We got single bond, and then double bond to carbon. We list those twice. Now we go down the line and we see until we get a winner. Look at the first, carbon versus carbon. There's no winner. Carbon versus H. Now we have a winner. And thus, this is going to be the high priority group. The high priority groups are on the same side, and tamoxifen is Z. This down here should be the other one, which is going to be E. Oxygen, phenyl. They're opposite E. Okay? Now we can note that in the Z configuration, the Z stereoisomer, this compound has activity against breast cancer, but the E configuration, the E stereoisomer, is inactive or not active against breast cancer. Thus illustrating the importance of stereochemistry and the orientation of these groups, in this case relative to each other. Okay, let's do some more examples of E and Z. Particularly when you have to sort of keep going out the chain, like we did with that tamoxifen example. Well, sort of already said this, but if the first atom is both the same, that is, if you're undecided, we have to then look at all atoms directly bonded to the atom bonded to the alkene. That's what we just did with tamoxifen. Let's do that again here. Is this E or Z? How about on this end? Oxygen or sulfur? We're looking at the atoms bonded to the carbon first. Well, we have a winner. Sulfur, higher atomic number. How about over here? Carbon or carbon? Well, it's the same. So when it's the same and it's undecided, what do? We look at atoms directly bonded to these atoms. What's bonded to this carbon? Let's list it here. High priority first. Carbon, carbon, and an undrawn H. C, C, H. What's bonded to this carbon? Carbon and two H's. Carbon, H, H. That guy. We listed these high priority first. Now we go down the line and see until we get a winner. Which is better, carbon or carbon? No win. Carbon or H? We get a winner right here. This is your high priority group. They're on the same side, and that is Z. Common mistake that students make here is they see this big iodine out here and say, hey, that's a high priority group because it's got a high atomic number. No, we don't consider the iodine out there. We consider one atom at a time, and then when we get out here, we consider what's on that atom. The iodine's not on that atom. This is how we do it. Let's do the one over here. Basically, what we can take here is, let's do this example here. What's on this carbon? Carbon or carbon? Okay? Well, what's on this carbon? What's bonded to that carbon? The three bonds. Not counting that back over the three this way. HHH. What's bonded to this carbon? CHH. CHH. The C beats the H, this is your high priority group. Basically what we can take from this, anytime you just have alkyl groups, the longer alkyl group is going to be your high priority group. Because eventually you'll get to a point where that one just has H's on the end, where this one's got one more carbon on the end and beats all your H's. How about on this side? Carbon or carbon? Well, it's the same. So we have to look what's bonded to the carbon. What's bonded to this carbon up here? Iodine, H, and H. What's bonded to this carbon here? Bromine, bromine, and H. Which one's high priority group? Look at the first. Iodine beats bromine, high priority group. Because the high priority groups are all the same side, this one here is also Z. Don't fall in the trap of saying, hey, this has two big groups on it. No, it's sort of like ace is high. An ace and two deuces beats two kings and a deuce. Okay? So we want to look at the first thing first. That beats this. Let's look at the last example. This example is just going to take us out a little bit further over here. On this end, F or H will be F. On this end, carbon or carbon? Well, you got to look at what it's bonded to. This carbon is bonded to HH and C, so CHH. This carbon is bonded to CHH. Basically, that's both CH2. We need to move out. This carbon is bonded to chlorine HH, where this carbon, the second carbon, is bonded to carbon HH. Here we get a winner. Chlorine beats carbon, and so this is your high priority group, and that is also Z. Seems like most of the examples ended up being Z. It's just by coincidence. This bromine doesn't get counted way out there. One atom at a time, and on the second carbon, it has a chlorine attached where that one only has a carbon attached. Z. Now again, if we can label something as Z, that means there's also an E. That would be Z. The E would look like instead of the fluorine being cis to the chlorine substituent, it'll be trans to it. And so this would be E, because we got the F in the high priority group here, opposite. These would have the same exact name. Otherwise, you can name this. That's the same exact name. This just has Z in the front of it. This has E in the front of it. Stereoisomers. This alkene is stereogenic. But we knew that because if you can label it as Z, that means there's also an E. There's two stereoisomers. But in the cases like those up there, we could not do an E or Z. That tells us there's no stereoisomer. It's not stereogenic. One miscellaneous point here. When you have a double bond in a small ring that is less than like about 9 or 10 carbons, your standard rings 4, 5, 6, this alkene cannot be stereogenic. That is, this cannot be trans. You cannot draw this ring like this. This bond has to come this way to make the ring. It cannot go the other way with the methyl coming this way. You could not draw this compound like this. The methyl and the chlorine have to be on the same side because the ring is on the other side. Okay? This is not possible. Now if you get a big ring, this starts to become possible. Maybe 10, 12 size ring. Certainly a 6-membered ring, 5-membered, 6-membered ring. The alkene is not stereogenic. And so we would not consider stereoisomers about that particular alkene. Okay, I'll finish up nomenclature by looking at the very back. This is a news article about some refrigerants. A lot of your refrigerants are gases. You're familiar with Freon. Many of these are alkenes. And here's some examples of more modern day refrigerants. What you can do is you can just look and kind of check your name. Don't look at the name. Name this. This one here is called trans. Okay, they have a stereochemical descriptor. We see the groups are trans about the double bond. There, we have a trans here. Note that this guy here, there's no stereochemical descriptor. That's because that alkene is not stereogenic. Okay, if you try to do E or Z, you will not get an answer. By the way, with two groups, you can use cis or trans. It works. But you can also use E or Z. Trans would also be known as E or opposite. Of course, if we did the priorities here, on this carbon, F or H would be F. Over here, H or carbon would be carbon. And so you see they're opposite about the double bond. Trans will work. We could also use E. When you get to 3 and 4 substituents on an alkene, cis or trans does not work anymore. It becomes ambiguous. And so then you need to go strictly with the E and Z. Of course, if there's only one substituent on an alkene, you'll see that it's not stereogenic, and there's no need for worrying about cis or trans or E or Z. Okay, so that's stereochemistry of alkenes.